This video is for section 6-6, quadratic functions that have this formula, the variable y alone, and then on the right side, this pattern, where the letters a, h, and k are specific numbers. Compare the values of functions s and h in the chart below. Function s is x squared, but function h is x squared plus 5. When you use different numbers of x in those function equations, it produces these answers. When x is -3, x squared is 9, but x squared plus 5 is 5 more than 9, or 14. And you'll notice that in every row, the value of function h is 5 more than the value of function s. When you look at the graph, the parabola that has a vertex at the origin is function s. The parabola that has a vertex 5 units above that is function h. Notice that h is 5 more than s of x, so you can fill 5 in on the blank. The vertex of function h is the point 0, positive 5. It is 5 units higher than 0, 0. True or false? H of x is similar to s of x, but it is 5 units above s of x. That's true. What can you conclude about the graph of function L if its equation is y equals x squared minus 5? We could conclude that it is a parabola that is 5 units below the parabola for function s. The following table shows solutions to f of x equals x minus 2 squared. For example, when x is replaced by -1, the value of f is positive 9. These dots are graphed to create the parabola on the right that has a vertex at the point 2, 0. Notice that the minimum value of 0 occurs when x is 2. And notice that the axis of symmetry is the line x equals 2. That's a vertical line crossing the x-axis at 2. The side of the parabola to the left of that line is the mirror image of the right side of the parabola. True or false? F of x is similar to function s, but it is 2 units to the right of function s. That's true. What can you conclude about the graph of function m if this is its equation? Well, notice that this differs from the one we just looked at because this has a plus sign here instead of a minus sign. We can conclude that this is a parabola that is 2 units to the left of function s. Let's look at these examples one more time. When a constant term has been added on the end of the function equation, the parabola moves up. When a constant term has been subtracted from the end of an equation, the parabola moves down. When a number is subtracted from the variable x in the squared term, the parabola moves to the right. But when a number is added to the variable x in the squared term, the parabola moves to the left. Instead of looking at equations with numbers, let's create a general pattern that we can use for all quadratic functions. Here it is. This is called the vertex form of a quadratic function. The letter a, h, and k will be numbers, but the y and the x will stay as letters. For example, y equals 2 times x minus 3 squared plus 4 is a quadratic equation in vertex form. This form is useful because h, k is the vertex, and the equation x equal to h is the axis of symmetry. For the example I just wrote on the screen, the vertex is the point 3, 4. And the axis of symmetry is the line x equals 3. So you can see when we have an equation in this format, it is very easy to figure out the vertex and the axis of symmetry. Here's an example. Graph y equals negative x minus 3 squared plus 5. This is a quadratic equation, and it is in vertex form, where the value of a in front of the parentheses is the number -1. The value of h is the number 3, and the value of k is the number 5. To identify those values, we're simply matching up our equation to the basic pattern y equals a times x minus h squared plus k. With the value of h and k, we know what the vertex is. It is the point 3, 5. And we can graph that dot. Over 3 up 5, right there's the vertex. We can also find the axis of symmetry. It is the line x equals 3. And so we can draw a vertical line crossing the x-axis at 3. And as expected, the vertex is on the axis of symmetry. Because a is a negative number, the vertex is a maximum. If the vertex is a maximum, then the parabola is this shape, where the vertex is the highest point on the parabola. So let's go over to our grid and build the parabola. From the vertex, left 1, down 1, and its matching point over here. Then from the vertex, left 2, down 4, and its matching point over here. Then from the vertex, left 3, down 9, and its corresponding point over here. Then draw in the branches to make the parabola. If you're wondering how I got the additional dots on the parabola without taking the time to make a table of values, then here's what I did. I ignored the 3 and the 5 because I had used those values to figure out the vertex. And instead, I focused solely on the fact that this is a quadratic equation where the x gets squared, and then in front of that, it's multiplied by -1. I asked myself, what happens to y if from the vertex, x changes by 1 unit? 1 squared is 1, and then timesing by -1 is -1. So when x changes by 1 unit, the y changes by -1. That gets me these 2 dots. Then I asked myself, from the vertex, what if x had changed by 2 units? 2 squared is 4, and there's a negative in front of that, which is -4. So from the vertex, when x changes by 2, the y changes by -4, which gets me this dot and this dot. Then I asked myself, from the vertex, what if x changed by 3? 3 squared is 9, and the negative in front makes -9. So I went over 3 and counted down 9, which got me this dot and this dot. So the value of the h and the k gets you started by finding the vertex. The value of a lets you know whether the parabola is opening upwards or opening downwards like this one does. And you can find other dots on the parabola by squaring values of x and multiplying by the value of a. Let's try one more example where we put all those skills into effect. Graph y equals 1/3 times x plus 1 squared. This can be converted to vertex form like this. Y equals 1/3 times x subtract -1, and then the squared. where this is a, the -1 is the h, and the k is a 0. From this form, we know the vertex. h comma k is -1 0. And we know the axis of symmetry is x equal -1. That helps us to build the graph. -1 0 is located here, and we draw a vertical line through it to be the axis of symmetry. Because a is positive, that vertex is a minimum point, meaning the parabola opens upwards. It has this shape. Let's draw the parabola by finding some dots on the branches of the parabola. When x changes by 1, and you square it and then times by 1/3, what do you get? You get 1/3. So on the grid, when you change x by 1 unit, you only go up 1/3 of a unit. And you can find a corresponding dot here. If you use 2 for x and square it and times by 1/3, you get 4/3 or 1 1/3. So from the vertex, when you go 2 units to the right, you want to go up 1 1/3 units. And there will be a corresponding dot here. These are on the same level of the paper. For better accuracy, let's do this one more time. Use a 3 for x, square it because this is quadratic, and times by the value of a. 3 squared is 9, and 1/3 of 9 is 3. So from the vertex, when you move to the right 3 units, you would go up 3 units. And the same to the left. Draw in the branches, and you will have the parabola. Let's summarize the lesson. We discussed how to graph a parabola when the equation is in a particular format called vertex form. First, find the vertex. Second, draw a vertical line through the vertex called the axis of symmetry. Third, figure out whether the vertex is a minimum or maximum so you know if the parabola opens upward or opens downward. And fourth, figure out dots on the sides of the parabola by squaring 1 and timesing by the value of a, then squaring 2 and timesing by the value of a, and then squaring 3 and times by the value of a. That technique is equivalent to figuring out an XY table, filling in the vertex, and then choosing numbers that are to the left and to the right of that vertex. Counting to the left from -1 would be -2, -3, and -4. To the right from -1 are 0, 1, and 2. Then take every one of these numbers for x and substitute it into the equation. For the problem we just did, we would go 1/3 times -4 plus 1 squared and figure out this answer. It turns out to be 3. Repeat this process for all of these rows of the table. I'm sure you noticed that the technique I explained is faster than filling out a table to get the dots on the parabola.